Hi, am I audible?
Yeah, you are.
I will make you guys the host. Zoe, I'm making you the host. That's okay? At 11:25, we can start admitting people. Do we have everybody here? Sakshi is here, Shreya, Tista. Who's missing?
Anusha's not coming.
Okay. Zoe, can you enable Anusha? Can you admit Anusha? All the best, girls.
Thank you.
Thank you.
Thank you.
Hello.
So it's sharp 11:30. Do I start talking or do I wait 5 minutes?
Am I audible? You can see the screen, right?
Your voice is breaking.
Hello. You can see the screen, right? Hello.
Yeah, we can see the screen.
Does anyone want to do a mic test?
Good morning, sir.
Good morning, sir.
Hi, we will be starting at 11:30 sharp. It's so we'll have to just wait for another 3-4 minutes.
Okay, ma'am.
We'll start in a minute or two. Good morning, everyone. Thanks for joining in. We'll start in a minute or two.
Okay, ma'am.
Okay, ma'am.
Hello, everyone, and welcome to the TIS Capgemini Innovate for Tomorrow contest, a STEM pre-event for India Internet Governance Forum (IIGF), put together by the Innovation Story team in collaboration with Capgemini. My name is Tista, and I will be one of your moderators for today. Before we start, if you have any questions, please do add them on the chat box, and our moderators will pick them up. And if time permits, we will answer them. Do not worry, all your questions will be answered. We will update them in the FAQ section on our website at theinnovationstory.com during the entire duration of this challenge. We have a packed agenda for today, so let's jump right in.
Good morning, ma'am.
We are from the Innovation Story. Everyone, please be muted. We are from the Innovation Story, a launchpad to equip young people with the skills needed to transform them into innovators and change makers. The focus is on experiential learning in science, technology, engineering, and mathematics. Through hands-on experiences, the program inspires students to pursue careers in robotics, software design, engineering, programming, and animation. As part of that, we are proud to launch the TIS Capgemini Innovate for Tomorrow contest, where your ideas matter. STEM jobs are laying the foundation for the future and solving the world's greatest challenges. As we launch this contest, we cannot wait to come across exciting and innovative solutions in the world of STEM. The Innovation Challenge is brought to you up by the Innovation Story and sponsored by Capgemini with a team of experts from aerial, underwater, and terrestrial fields, who you will be hearing from shortly. We thank all of them for taking out the time today and helping bring this together. Through this challenge, students will have the opportunity to devise innovative robot-based solutions to real-world problems with mentorship from industry experts.
Hi, I'm Shreya. I'm from the Dhirubhai Ambani International School, and now I will be taking you through the phases of this challenge. So, for the first phase of this challenge, all participants will have to identify a problem in one of the three categories, which are aerial, underwater, terrestrial, and terrestrial. And terrestrial. They have to work with their team and devise a robot-based solution to their chosen problem, and they have around 2 weeks to do this, from October 3rd to October 15th. They will have to describe the solution in a 3-minute video submission. When the portal opens up for submission, please upload a video of the solution and answer a few questions. We will have these notices put up on our Insta page and website, so keep checking when the portal opens. The deadline for submission is October 15th at 11:45 p.m. IST. Then, after diligently being assessed by a panel of esteemed judges and experts, we will select 30 ideas, and those will be eligible to move on to phase 2. We will announce the names of the 30 teams on the website on 18th October. In phase 2 of the challenge, the 30 shortlisted teams will have 2 weeks, that is, between October 19th and October 29th, to work with a mentor and develop their ideas. They will enhance their solution with the help of mentors from the industry and other experts who will give them feedback and direction on a regular basis. The teams will then present an improved pitch to the judges over a 15-minute Zoom meeting on 30th and 31st October. The top 10 teams win exciting prizes, and this competition opens up a world of opportunities for all the participants. They will receive mentorship opportunities, and all participants will be able to attend college readiness workshops with experts and students. All participants get participation certificates, and the top 10 will receive exciting prizes like AirPods, speakers, and Polaroid cameras. They will also have the opportunity to implement their proposed solution. I know I might be going quite fast right now, but don't worry. All of this information will be available on our website and our Instagram page, and you can get in touch with us for any questions through these channels or email us at reachout@theinnovationstory.com. Now, it is the time that we have all been waiting for. The 3 panels will host the experts. They will share some of their perspectives in their respective fields, and those should give you some ideas on what to work on, what to focus on as you build your problem statements and possible solutions. Now, without further ado, I will hand over to Anusha, who will moderate the underwater panel.
Hello, I'm Anusha Jain. Welcome to the underwater panel discussion. We have with us Mr. Tanuj Jhunjhunwala, co-founder of Planus Technologies. Mr. Tanuj Jhunjhunwala is an alumnus from IIT Madras with bachelor's in mechanical engineering and master's in product design. At Planus, he leads business development, international expansion, and marketing. As an engineering student at IIT Madras, Mr. Tanuj was involved in various interdisciplinary projects, and master's research earned him several awards. More recently, Mr. Tanuj was featured on the highly acclaimed Forbes 30 Under 30 2021 Asia list. Before I go to them, please do know that if you have any questions, feel free to post on the chat. We will try to address them if time permits. Else, we will get the answers and update on the website in the FAQ section.
Hi everyone, Tanuj here from Planet. Thank you so much for having me here today. I have a few slides to show that will talk a lot about what we do in underwater robotics and an exciting video to show at the end, also to walk you through the technology that is developed that is helping India in several ways. So this my screen is visible now. Yep. So Planis is a startup that started from a university called IIT Madras, which is in Chennai. And we build underwater drones. A lot of you would have seen aerial drones and will be hearing also about from the other panelists today. So underwater drones is a robotic device that goes underwater and can be used for different purposes. This is a project we did when we were students at college. And then over the years, this became a company. And now we are a 100-member strong team today. So we've been working on this technology for over 10 years now. So broadly, India has a lot of aging infrastructure. So infrastructure means we have roadways and railways. So India has a lot of fresh water, right? We have a lot of mountains, a lot of fresh water, and these waters form rivers. Now, due to the large population, the large area, all these rivers, we've built bridges so that cars and vehicles can go, and equally trains can go. So that leads to a lot of bridges. There are about more than 3 lakh bridges in India overall. That are there on the river crossing. Similarly, dams are built. Dams retain water used for hydroelectric generation, used for irrigation purposes, and it is a very big reservoir for providing water to several cities. So India has over 5,000 dams. Very lucky, India is very lucky to have so many dams, and so on. And lastly, since India has a very large coastline, we have a lot of ports because it becomes a lot of economic activity of ships coming in and taking cargo. So overall, these marine or underwater infrastructure will deteriorate with time, right? It's like a human body. All of us once in a while do fall sick, once in a while do have accidents, we do get fractures, and as the age progresses, the health issues become are expected to become more. Of course, some people are extremely healthy and some people are not. So overall, these assets that are so critical also age with time, and after some point of time, they will fail. And as you can see some photographs of bridges and dams failing, they lead to catastrophic failures, and that's a very big problem. This is not a problem only in India, in the world. This is a photograph from Amsterdam from last year. There are assets in Amsterdam that also collapse similarly. So today, these assets need to be checked. They need to be checked for defects, for cavities, what is going to happen because of which it's going to fail. And before that happens, it needs to be fixed. So today, divers do these inspections. So they go underwater with scuba gear, with cameras, sensors, and collect different data. But being human, going underwater is like going in space. You need a space suit there, so you need a suit here. And there are a lot of limitations because you can't go deep. The pressure will kill the person. You can't have unlimited oxygen supply because they cannot breathe through water. And of course, there is a lot of safety risk with all these parameters involved. So divers, human divers, have several limitations of going to high depths, capturing data that is useful for them, and then kind of relaying that to the experts to tell them what exactly is the problem. So with this as a background, we have, so these are some photographs of different divers in different cases. So that's when we come to a question of diver versus a machine. And on the right, you can see a diver. On the left, you can see a machine. So it's an underwater robot with a lot of capabilities on it. I'll show you a video of that later on. That can do a lot of the work the diver does there. And marine robotics is not new. It comes in all sizes, shape. On the left, you can see one is very big. In front of it, there's a very tiny one. It comes in different shapes, sizes. The yellow one in the middle is over 5 meters long. It comes as crawlers, it comes as amphibians, it comes as free floating. And on the right, you can see as big as a palm as well. So this is not new. The Titanic was found through using one of these. And this is typically the setup that happens. So you have the ROV, which is the remotely operated vehicle. It's the technical word for an underwater robot that is deployed. It is connected with a cable to a control station. And then you have a ROV pilot, like you have an airplane pilot. Similarly, there's an ROV pilot who controls the machine from a joystick, and engineers or experts can see the data live stream. And this can be done without dismantling the asset like a bridge. So the trains can go on, but the data collection still happens of the foundations and underwater structures. Very safe, very robust, a lot of sensors assisting in these robotic technologies. And there's no battery limitation because the cable brings it power from outside. So theoretically, we can go unlimited endurance is there. So, so these are the different parts of the robot. Sorry, I think there is some, yeah. So these are the different parts of the robot. As you can see, it's quite sophisticated. You have propellers, you have cameras, you have lights, you have manipulator arms. You have a lot of cabling, you have a chassis on which it's there. On the top, you have an emergency beacon to find it in case it gets lost or to know where it is. And so it is like a small transformer itself there. Yeah, and this is the setup. So on the top left, you see a control room. So this is the control room where the data comes in live. You have several monitors, screen, joystick. The controller is the operator's controlling. I think someone is drawing, so it'll be good if people don't draw on this so that it's visible to everyone. Then the cable comes to a launch and recovery system, which is a crane, and then it's deployed underwater, and then you can inspect submarines, underwater structures, and several things from it. So to think of it, the applications for this could be in offshore oil and gas. That's where you have a lot of underwater structures, and oil is very important today. We know the world is moving to more renewable energy as we speak, but as of today, oil is important, and these structures will lead to issues if these structures fail, like oil spills. So hence inspecting these are very important. Similarly, port structures, very important for movement of cargo around the world. Dams, I think I've given enough examples of dams, and bridges as well. So people from Mumbai know the importance of the sea link, and something happens to that, there is going to be a lot of discomfort on a daily basis there. So these are the different applications. Of course, there are more applications, like for defense purposes. Navy could use this for coastal monitoring and coastal ways. Secondly, you could do a lot of environment monitoring with these technologies for underwater data collection, seismic activity, and so on there. So that is the different use cases. Some photographs. So our small company has been using this for the Indian Railways. As you can see, these bridges are very old. They were built by the Britishers, and we use some small vehicles, small boats, on which we set up these systems. On the left bottom, you can see that photograph. Our operator is controlling with a PlayStation joystick on a small screen, and we install this, and we move the robot in water, collect different data. Those are the robots we have built on the top right. Some much smaller versions, about 50, 60 kgs they weigh. This was again for highway bridges. We can do the same thing. Again, very old bridges, as you can see, arch bridges these are. And we've also done some work for some customers abroad. So these type of structures are not seen in India majorly, but these are local municipalities that have these assets here. So these are the real use cases where our technology has been done. And to a little bit talk about us. So we started off as a small lab in a dungeon in our campus. And then this was one of our first products we built that went to the field. And it was a good journey of learning, experiments, and field execution. So without any ado, I have my last video here that I'm going to play. So So this is talks about bridges. So as India has several bridges, these are some unfortunate cases that have happened in the past, where bridges have gone down. And as Planis, we have built these systems that can help in detecting or testing underwater. So these robots go underwater, they can see defects. We can go long inside pipelines. As I mentioned, it is very safe to use these machines and much better and accurate than a human collecting data. The robot has several parts to it: the propellers, the cameras, different sensors. As you can see, it is a very small machine. A two-man crew can leave it in water, and then the pilot controls it with a joystick from the outside, and it self-propels itself. It is neutrally buoyant. We can go up to 120 meters of depth, which is more than 350 feet. And that's how the setup works for controlling this. These are actual defects or when while testing these assets. So imagine you're driving on a bridge and the bridge has these issues. So of course, it's a big concern to anyone, right? It's a public health safety problem that if something happens to the bridge, there will be a catastrophic failure. So we have done a lot of these bridge inspections, and we help authorities like the Indian Railways take measures. So we have lasers which allow us to size the defects. Indian waters are very murky, so we've built technology to do inspections in murky waters. So this is basically innovating as we go along. We can also check what is happening on the bed of the sea, of the river, and inform authorities if there are any unidentified objects. And yeah, these are different tests. I'll just skip this in interest of time. I'll just play another video. Yeah. So this is a video that'll give you an estimation of our facility. So we have our own pool in our office where our technology is built. So this is what it takes to build robotic technology as the company gets older, to give everyone on the call an understanding. So we have people who do a lot of electronics. So these systems are designed, developed. A lot of expertise goes from computer science to electronics to mechanical engineering, and core competencies like physics and mathematics is the basis of everything here. So so these are some close-ups of how these operations are done to give you a better perspective. So as I mentioned, they have lights on them, they have cameras on them, and on field we deploy them. A lot of safety is there. Even outside water, our people wear a lot of safety gear. So we can go up to 120 meters of depth. It has several sensors into it: carrying capacities, altimeter, sonar is a very commonly used sensor, and there's a lot of data capturing that is done from different sensors, like anchor chains for offshore platforms is of interest, because if the anchor chain breaks, again, the offshore platform is at risk. Then once the data comes in, there's a lot of artificial intelligence, a lot of image processing, a lot of new age technologies that are put into this for further analysis and further interpretation of data. And then that is submitted to the authorities for the decision making for repairs and maintenance. So yes, that is Planis. That is what we do. That is what our robots do in India. And we are very proud to be helping Indian authorities in India as a company in maintaining their assets. So thank you so much for having me. And I'm happy to answer any questions.
Mr. Tanuj, we have a question from one of the students. How are the ROVs able to handle the pressure of the water deep down the sea? What is something the ROV has to handle the pressure that a human diver doesn't?
Right. So what happens is all the technologies of the ROV, the electronics, goes inside a metallic or a plastic hull, as they call it. And the hull is basically a cylindrical object that is capped, waterproof. So we design it with the right material, aluminum, steel, and then as depths increase, there's platinum or titanium that could also be used. So we design it. It's an engineering design to ensure it is waterproof and water doesn't penetrate through. So that is how we make it waterproof. Like submarines also, right? Submarines go underwater, so they are waterproof. So there's a lot of engineering there. Secondly, a human diver can go up to depths of about 20 to 30 meters because the human body cannot handle pressure. There are some sophisticated diving which wear external suits that can go even up to 100 meters, but it is extremely skilled, extremely risky, and there are very few people in the world who can do that. But ROVs can go up to 6 kilometers of depth, which is, as you know, 100 meters for a diver and 6,000 meters or 6 kilometers for a machine. And 6,000 meters is what has been till now done, because I think the deepest part of the ocean they've gone to is 6,000 meters. So it can be designed for whatever depth. It's all about engineering at the back end. So hope I've answered your question. Happy to answer any more questions.
We have another question from Karthik Sarvesh. Will the sensor's radiation affect marine life?
No, it doesn't affect the marine life. It does create some noise, but it does not affect it beyond that. So we are intrusive to their environment, but we don't touch them and we don't affect them. It's just a little bit noise in the water we create with our propellers. But that's a short period of time. Apart from that, there is no radiation from these devices. And how many people control the ROV? There are about 2 people who control the ROV and 2 people who are support engineers. So it's a 4-man crew, as we call it, who go to the field and collect data.
We have another question from Siddhant Singh. What if the underwater robots have gone deeper than their limits?
Can you repeat that? Can you please repeat that, Anusha?
What if the underwater robots have gone deeper than their limits?
So it is defined for a factor of safety. So sometimes it's 2, sometimes it's 3. So what that means is that we are designing it for 500 meters or 1,000 meters. But if the factor of safety is 2, we divide it by 2 and we only operate it for half of that. So the operating depth of that machine is 250 meters, but it is designed for 500 meters with a factor of safety. So of course, if you breach that, there is a risk and the buyer who has the machine can lose his machine. So the standard operating conditions have to be met. It's similar to give an analogy, you all, like there are cars, right? Everyone knows SUVs you can probably drive in a desert, right? In a desert, you can take an SUV, but you can't take a small sedan in an SUV in a desert. So it's something like that. You design it for a certain application and put the terms and conditions. And if the user is overusing it, then probably they will lose the machine after some point of time beyond a factor of safety. So factor of safety is something that is put in from the engineering point of view.
Thanks a lot, Mr. Tanuj. As students, we completely understand and appreciate all that you spoke about, and we are quite keen to see how the teams address some of these issues. I will now hand over to Tista, who will moderate the terrestrial panel.
Hello all and welcome to the terrestrial panel discussion. We have with us Mr. Aseem Bhalera. Mr. Aseem Bhalera has a master's in computer science from the University of Southern California and a master's in mechanical engineering design from Santa Clara University. He's previously led engineering teams in the US, building unmanned aerial vehicles, autonomous underwater vehicles, and robots for minimally invasive surgery. Mr. Aseem founded Fluid Robotics to help cities across the world tackle urban water pollution. Thank you so much for your time today. Again, if you have any questions during the course of this discussion, feel free to post them on the chat. We'll get them answered if time permits.
Thank you so much for the introduction, Tissa. I'm just going to share my screen. Please let me know when you see it.
Yeah, we can see.
Is it visible? Okay, perfect. Yeah, thanks a lot for this opportunity to the Innovation Story team for allowing me to speak on this topic. And I've been involved in robotics for quite some time, and just how Tanuj mentioned, and I'm a huge fan of Planis, there's a lot of overlap between the different applications of technology of robotics. So if I'll talk a little bit about terrestrial robotics, mobile robotics that tend to stay on the ground. Don't go underwater, don't fly. But there are several applications that are covered in terrestrial robotics. So what I'll do is I'll walk through a few different types of robotic systems that come under this specific area, and I'll go into a little bit of detail about one of these applications. I'm sure all of you are aware of self-driving cars. So I'll get into a little bit of that in that area. So what really is a robot? It's an autonomous machine that can identify its surroundings. So it's present somewhere, right? It's solving some problem. So it has to understand its surroundings, and it has to navigate around in that environment, taking into consideration, obstacles, anything that can potentially impact the machine's safety, right? And it has to be able to do this on its own. There are obviously robots where you do have the ability to then begin manual control, underwater, aerial, even ground systems, terrestrial systems, all have a mode where you can come in and start manually controlling these devices, right? With the classic definition of a robotic system is something that can take decisions on its own based on what it sees around it and what its objective really is. So I'll show you a few different examples of terrestrial systems, of robotic systems that have been developed over the last several years, maybe even a couple of decades. So this is one such system. Humanoid robotics is a big field. I'm sure some of you have seen videos of a company called Boston Dynamics, based out of the US, where they do build humanoid robotics as well as robotics, multi-legged robotic systems as well. So this is one such system, extremely complex. We take our body for granted. When we are able to do complex tasks like walking up and down stairs, jumping off chairs, running around, running over obstacles, it's something that we humans take for granted. And when you come down to actually teaching a machine and building a machine to do something like that, you truly understand how lucky we are as human beings, being able to do these kinds of complex activities that otherwise would not have been possible. This is a multi-legged system. It's again built by this company Boston Dynamics. However, it's called the little dog. It's been used for many research projects across different universities around the world. This is a specific clip from a lab in the University of Southern California, where I was back in 2005. And this system, is being trained to navigate across very complex environments. And you can see, how difficult it is for the system. And this video is about, I'd say, about 10 years old. The system walking up and down steps, trying to navigate around, complex, obstacles like rocks, etc. And you can see how it struggles. And it's there's a huge, a very long process of you being able to learn how to do these things, over, testing over and over again. But this is one other application of terrestrial mobile robotics. So this is actually, this is one of my favorite videos, and it's from a competition that is run every year. This is called the Darpa Grand Challenge. It's run by the Defense Department in the US. This is one specifically from the year 2005, where there was a challenge for universities and other organizations to build autonomous cars to navigate across a 200-kilometer off-road course. It's a very complex environment. You can see, this specific car is the one that won the competition. It's called Stanley from Stanford University, and these red Humvees are actually from Carnegie Mellon University, and they came in second and third. And this is, one competition that actually, generated a lot of interest in self-driving technology. As you can see, these machines with these big sensors, all around them, being able to sense the environment, take certain decisions on where to turn, whether to speed up or slow down, and what to do based on the kind of input, based on the kind of software that was written by these engineers. So this is a very interesting application, and people build all kinds of different cars and vehicles to tackle this specific problem. Here's another photo of a multi-legged robotic system that can navigate complex environments. So you saw the little dog with four legs. This one has 6 and can actually do slightly more complex control and navigation. This is one another application that we build at Fluid Robotics. This is a robotic system that we send inside of pipelines underground. So if you're in one of the major cities, Mumbai, Delhi, Bangalore, we have these robots traveling underground, without anybody noticing, going around gathering data about the health of pipelines and the health of the underground infrastructure to help cities better manage that infrastructure. And here's something that is very exciting, for myself, for the Innovation Story team as well. This is a terrestrial robot, again, that's designed by school students, that are as old as all of you guys. This is for the first robotics competition, the FRC competition, where robots are built by students to solve different kinds of problems. So you can see the robot here navigating across a complex environment, able to pick and place objects, and do all kinds of complex maneuvers. So this is also a very interesting application and a very interesting robotic design that students can build. So coming back to the definition of what a robot is, it's an autonomous machine that can identify its surroundings, right? So how does a machine identify its surroundings? It does that using sensors, right? So this is a short video of one of Google's first self-driving cars. It's a Toyota Prius. This person, who tested it actually cannot see. He's just sitting there and he's, going for the ride. So the robot is, you can see the thing that's spinning on top. That's a sensor that includes, a camera. It includes something called as a Lidar that is used to sense the environment, right? So it's very important for robots to be able to understand the environment, to be able to sense it. So if I head here, my screen's a little stuck. Yeah. So, what is a LiDAR? A LiDAR is basically a sensor that uses light, pulsed light, to measure distances. So what you see on the top here in the car, this is a more miniature, cost-effective version of a LiDAR that anybody can purchase and use. It basically sends, light beams. It spins, so it can, scan in 360 degrees. And based on the reflected light that comes back to the sensor, it can identify, basic obstacles that are present in its path. And this is the technology that a lot of robots, including self-driving cars, use for being able to sense the environment. So, what is a self-driving car, right? It has a bunch of sensors like this to sense the environment, and it has basic controls, right? It has a steering wheel, it has a brake, it has brakes, it has an accelerator, so it's able to control the motion based on whatever input it is getting. So, once you start monitoring the environment, once you start getting Lidar data, or once the camera starts taking photographs, you have to teach the car, you have to teach the software that runs on the car to be able to recognize what is in its environment, to be able to take the right kind of decision. So if it sees, a car in front, it should stop. If it sees a traffic light that's red, it should stop. If it turns green, it should move. If it sees a person that's crossing the street, again, it should stop. So all of these things that all of these decisions that it has to make are based on how it perceives the environment and what kind of logic is built in its decision making. So machine learning, neural networks is one way to train a robot, to train the software that runs on the robot to be able to identify objects, classify them as a person or a car or a bus or a traffic light or a building or a zebra crossing, right? So it's a combination of a hardware system, which is the device, the car, the electronics that run on it, and intelligent software that helps it make the right kind of decisions. And moving on to the last point, right? It has to move around in this environment. Obviously, you have brakes, you have a steering wheel, you have wheels, accelerator. But how does it make those decisions? And there's a very simple concept of a control system. You have on the left here, you have a desired state in which the car needs to perform. It is getting input from its sensors, and it takes the input from the sensors. It takes what is the desired state, which is, if it's green, no obstacles, keep moving at a safe speed. That's a desired state. So based on sensor input, it has to I'd say modify the way it performs. So it could, if there's an obstacle, it will control its steering. If it needs to stop, it will apply the brakes and so on and so forth. And then the car moves on to the next state. And this keeps happening in a feedback loop as the car keeps driving itself continuously from one place to another. So, the takeaway here is that, robotic systems are very complex, very interesting, requires good knowledge of physics and mathematics to be able to build. But with today's open information age, you have all the information that you need to build one of these systems. So with that, I'll stop this presentation. I'd love to answer any questions that you might have.
Yes, Mr. Seem. So here are some questions.
Sure.
So this is asked by Lavanya. So with the help of this technique, can we build artificial hands or legs which can work like a normal hand or leg for the handicaps?
Yes, so there are many different ways that can be done. At the core, the technologies are very similar. You do have sensors. These sensors could be sensors that are taking in input from the human itself. There are robotic arms that take in information from the human through brain activity, or it could be something as simple as a cane that a person uses with a small lidar in the front that can detect obstacles, that alerts the user, okay, there's something coming, take a step up, right? So there are different ways that can be that such problems can be solved, but at the core, it's the exact same kind of logic. You have sensors, you have a system that's taking that input, and taking certain decisions. And the decision could be alerting the person. It could be actually controlling an arm, opening your arm, hand and closing it, or your fist and closing it. So yes, at the core, it's very similar. Obviously, different kinds of problems would be encountered in that case. But yeah, I hope that answers your question.
Thank you so much. There's one more question by Vardita Singh. So how do engineers manage to engineer robots for Mars when the environment is so different with respect to gravity?
Good question. So, it's all done in a simulated environment, right? You create simulations, and just how you build an underwater robot, or you build a robot that has to go 6 kilometers underwater, or a robot that needs to fly. At the very first steps are to create simulations, and with today's technologies, you can create simulations on a computer and feed it the kind of information that you would expect to have, in a place like Mars, right? The gravity is different, but a lot of testing that's done is done in the desert, in different countries where the terrain is very similar, right? The systems eventually have to perform certain tasks for uh, which are driven by the objective of sending a robot to Mars. Why do you want to send it? You may want to check for water. You may want to get samples back to Earth and test them. So those kinds of objectives are fulfilled based on whatever the requirement is. But the most common way to deploy robots for new applications is to build simulations. And I actually worked prior to starting fluid robotics, worked in surgical robotics. So we would build a robot to perform surgery, but before we could even go in and actually test it on a human being, there are many other ways where you could simulate a surgery, get it to a point where it's not going to fail, and then you actually bring in the humans, or send the robot off to another planet. So yeah.
Thank you so much, Mr. Asim. I'm sure the participants will benefit a lot from this discussion. Now I'll hand it off to Sakshi for the next panel of Aerial of the webinar.
Thank you.
Hello all and welcome to the Aerial panel discussion. We have with us Dr. Apurva Joshi. Dr. Joshi graduated with PhD from IIT Bombay and Monash University. His research was based on modeling and control of multi-agent systems. He has been working on several problems like drone-based aerial logistics, autonomous complex mission planning for drone fleet, and vision-based identification, as well as tracking. Before we move ahead, please do note that if you have any questions, feel free to post them on the chat. We will try to address them if time permits, else you will receive all your answers and updates on the website. Over to you, Dr. Joshi.
Hi, thanks, Sakshi. Let me just share my screen. Can you guys see? Sakshi, is my screen visible?
Yes.
Okay, so thanks EIS for giving me this opportunity to interact with all the youngsters who for the future and will take this domain ahead. So this talk is basically about aerial robotics and what sort of applications you can work on using aerial robots. So I work as a research scientist at IIT Bombay. I'll talk about some of the work there and also do some consultancy and development work under 301 Labs. So the history of unmanned aerial robots or aerial vehicles has a very long background. It started back in 1918 when the first sort of Wright brothers developed their first airplane, and they started understanding aerodynamics. But the problem back then was that there were a lot of fatal crashes that killed a lot of pilots. So for the testing phase, they wanted to make something that is not harmful to humans. So they started building automatic planes, believe it or not, back in 1918. Then came World War II, wherein they wanted to practice firing at enemies. So that led to the design of target drones back in 1941. Then there was a space race, and then we had satellites going into orbit and communicating back to the stations back on Earth. That was back in 1957. And this is when we sort of understood the mechanical aspects pretty decently about flying vehicles. And then it was about the electronics revolution. So then there was microcontrollers, which became small, kept getting smaller and smaller, and still are getting smaller by the day. There were microcontrollers which were first made in the 1970s, and then that led to the rise of intelligence in all these machines. Then there was internet, which is now called IoT, which connects all these devices together. And there's also led to a huge open source community where there is a lot of information sharing, and there's a lot of development that can be done, and you can build on each other's work. So what's next, right? That's up to you guys, and we're here to motivate you to do that. So what are the types of drones or unmanned aerial vehicles that you can use these days? So these are different configurations of different vehicles that you can see. The first one over here is a multicopter, which essentially is a bunch of motors with propellers attached to them, and the way in which you control the speeds of this motor leads to motion of this vehicle. So it has the ability to hover in one place, and that can be useful for several applications that we can see or in the coming slides. So one problem with this vehicle is that it's very power hungry. That's why we have other configurations that suit different applications. For example, you have a fixed wing aeroplane. So sorry. Okay, so I'm just going to continue. There's a fixed wing so these are fixed wing vehicles, and these are predominantly for longer endurance and achieving longer range sort of missions. These can't really hover in place, and they also need a runway to land and take off. So to overcome such issues, there are something called a hybrid vertical takeoff landing sort of vehicles. So the one you see the bottom left over here is a vehicle wherein the fuselage, that is the body of the vehicle, remains stationary, and only the only the wings of the airplane are able to rotate so that they can take off vertically and then transition into a fixed wing sort of flight and move ahead. So that's one configuration. Then another configuration is this over here, wherein the entire, if you can see, it looks like a fixed wing, but it's standing vertical. So what it does is it takes off vertically and then transitions its entire body and then starts flying horizontally. So that's Asim touched upon it, and that's the beauty of control systems. So you control using different sensors how you want the vehicle to behave, and you get it done. Then there are other applications where you need stealth. So you have something like this, which is very similar to a helicopter, but also very miniature, so that you can fly past things undetected. And then there's also, if you must be knowing that there's recently a helicopter that is operating on Mars. Right, so this is a coaxial type of helicopter. You can see on the same axis there are two propellers, and what that leads to is better efficiency compared to the other designs, and it can also hover in place. And also talking to the rover called the Perseverance rover on Mars, and it helps the robot communicate, helps the ground robot plan its path, giving it a third dimensional perspective of the terrain on which it is operating. So if you noticed, there are vehicles that I talked about, and these vehicles can carry different payloads. Payloads essentially are different sorts of sensors, different sorts of things that can be useful for different applications, and that's about how creative you get with it, and that leads to the solution in different sort of applications. Right. So, for example, then you have drones which have a camera, and then they are used by tourists and people to take selfies, and for wedding photography or photography of major events, so on and so forth. So if you replace the camera, there are different types of camera that are available. For example, you can see over here, this is a multi-spectral camera. So what this multi-spectral camera does is it gathers information over a bigger spectrum of the electromagnetic waves, just like a camera, but just a wider range, and that can lead to getting information. For example, regarding the health of crops. So you can see over here, this is a drone which has this sort of camera on board, and it has mapped a field, and the red parts indicate diseased crops, for example. Then you can have payloads which are thermal cameras plus infrared cameras, and that can be useful for missions like search and rescue. So for example, this is an image of people who got lost on a trek, and they were able to find these people using these thermal cameras, right? Then there are drones that can carry water or pesticide or fertilizer to spray on top of crops. And this has given a huge boost to productivity in agriculture. It can be used to spray stuff on, for example, coconut or areca nut trees, which is very difficult without a drone. So those are some new applications in which drones are really carving a niche and helping out in the agricultural sector. And they also serve a lot of they are of great help in the surveying industry, and also in infrastructure management. So for example, I think Asim and Tanuj talked a bit about that, how about how the ground robots and underwater robots are useful for similar tasks. Even drones are used for, so over here you can see it's surveilling a telecommunication tower. It can also be used to survey high voltage electric lines. It can be used to survey wind turbines. It can be used to survey oil pipelines or water pipelines for structural damage, so on and so forth. So those are some applications. Then there are some applications in which they are used for delivering medicines to very remote areas. So this is a company called Zipline, which is doing that in Africa. And there are some recent developments of that sort even in India. So they carry blood supplies, they carry vaccinations to remote areas which are difficult to reach using roads. Then there are some applications where they're used to rescue people, for example, they're used to fight fires. So the list is getting bigger and bigger by the day. So what's next, right? What's happening in the labs? That's where I do most of my work. Is that the sensors are getting better, so we can perceive the environment better. The computers are getting faster and smaller, so you can build more AI. You can train them to do better things and be more smart. And you can also, communication modules are enabling people to drones to talk to each other and take decisions based on what their neighbors are doing. So there's more cooperation between them, and that all leads to more autonomy, right? And they can interact with humans and do more things and smarter things and help humans in a lot of things. So for example, you can see on the top video over here in the top left. So this is a new sensor called an event sensor. So you can see that this guy tried to harm the drone by throwing a ball at it, but the drone was capable of detecting that something is thrown towards it. There's an obstacle, there's a dynamic and a fast moving obstacle coming towards it, and quickly changed its trajectory and avoided the collision. Right. So over here you can see on the top right, you have the first autonomous drone racing league that was launched, I think a year or two before, and they move as fast as 5 meters per second or 8 meters per second, and it's improving by the day. Then over here at the bottom, you have this robot which has an arm attached to it, and it's able to grasp objects, and it's leading to applications like robotic painting, or carrying or manipulating different things while you're in the air. Then we've done some work on cooperation before. So here, there's some work that I did on one person controlling multiple drones, formation flight. Then over here, you have a drone which is guarding a convoy of vehicles, a convoy of ground vehicles which are moving on the ground, but the vehicle on top is providing some sort of security to them, so that in case some threat arises on the ground, it can notify the people before something bad happens. And we've done some work on search and rescue, wherein multiple drones can be deployed in multiple areas, so that they can search for survivors. They and cooperatively cooperatives scan a bigger task, a bigger area than one single vehicle, so that you have you can cover a bigger area and provide more and quicker rescue packets to these people and deliver payloads to those in distress. Then on right, you have some drones building a bridge. This is some work done at ETH Zurich, which is still quite difficult to actually do in the real world, because over here they have a very good sense of where they are in the environment using motion capture cameras. But this is something that you will see very soon in the real world. Right. Then there are robots carrying bricks and building structures. Again, this is an indoor environment, and this is something that will transition to from lab to society really soon. So that's where I believe the future is. We need a lot of work by people who are motivated enough to work really hard on these problems. Like the other panelists said before, physics, maths, STEM essentially forms a really important role in making this successful, in taking stuff out from lab to society. And we need expertise from all sorts of domains in order to actually reach that goal. So there's, like I said, there was application in agriculture, in medicine, in disaster management, in logistics, in all sorts of fields. So it's wide open for everyone to be creative and really make an impact. So that's my talk. Thanks for your time. I hope you enjoyed it, and I'll be happy to take questions.
Okay, that was really, really informative, very nice. So we do have a few questions over here. One question is, are there any drones being developed without fans, or is there any development currently in that area?
So yeah, that's a good question, actually, quite creative. So as far as I know, one new development in the propulsion technology is ion-based thrusters. So it's called ionic propulsion. To be honest, I don't know too much about it, but that's mainly useful for drones in space, right? Not really in the atmosphere that we have on Earth. Though there is something interesting going on in ducted fans. So you don't just have a fan, but you create a duct around the fan, so that that creates it enhances the efficiency of the propulsion system.
Okay, wow, that was very nice. So also another question by Priya is, which sensors do you use for stability in the drone?
So essentially we use, it's like, you can think of it this way, it's like a smartphone without the screen, and it has an IMU, which is an inertial measurement unit, which comprises of an accelerometer and a gyroscope. And then we use magnetometers so the IMU tells you about what your orientation is. Then you have magnetometers, which tell you about what your orientation is with respect to the north of on Earth. Then you have barometers, which tell you your altitude. Then you have lidars that Asim talked about, which tell you your localization or where you are present in space. You have cameras. Then you have, yeah, that's about it actually. You can have some more, but then they're not used that frequently. But essentially, everything that you have on a phone is on a drone.
Yes. The last question we would be taking up today in the aerial panel would be, are there any government restrictions or prohibitions of operating drones?
Yes. So it's yes and no. Recently, as recent as last week, the government just released a map of where all you can fly without any permission. So please do visit Digital Sky, or just check out just search for Digital Sky on any of the search engines, and you will find all the restrictions that are in place. So restrictions are predominantly defined based on how big your vehicle is. So if you have a vehicle which is under 250 grams, you don't need any permission. You can fly it anywhere, but you can't fly it in sensitive areas. So sensitive areas are marked as a red zone on this interactive map that is on Digital Sky. And you don't have permissions unless you get specific exemption from government authorities to fly there. You can fly freely in green zones, that without permission.
Okay, great. Thank you so much, Dr. Joshi, for those great insights. We hope
you.
to see some of your points being addressed by the teams as they identify their problems and create solutions. So now I will hand over to Anusha for the talk on creative and design thinking for robotics. Thank you.
Awesome. Thank you.
After such an insightful session on all the categories, I would like to call upon Mr. Asim to have a talk on creative and design thinking for robotics.
Hi, Anusha. Are you able to see my screen?
Yes.
Okay, perfect.
Yeah.
Yeah, so, this is a discussion. I would like it to be a discussion. It's basically on, design thinking, what it is, and how it could be applied in robotics. So what I'm going to do is I'm going to structure this, talk into two buckets. One is looking at what design thinking is, and the second is an actual example of how we at Fluid Robotics implemented design thinking, the framework of design thinking when we started looking at solving certain problems in water pollution. So, design thinking is basically a framework for innovation. It gives you the, it gives you what the journey should look like when you go from, an idea to an innovation or to an actual invention. So typically there are 4 steps with an additional step that is part of the process, very regularly. So the journey involves, empathy. It involves the problem. It involves ideas about the problem and how to solve it. And then it actually involves implementation of those ideas. So typically these are the different steps that are part of the design thinking framework. And then testing is a very important part of design thinking that comes in multiple, it comes in at multiple times. So you test what you know about certain problems, and you test the prototypes, your ideas that become part of the end solution. So what we're going to do is we're going to go step by step, through this journey of design thinking, and then get into an actual case study. So, the definition of innovation, right? It's a practical implementation of an idea. So if you have just an idea, you can call it an innovative idea. But if it isn't implemented, if no action is taken to convert that idea into, something that can be built, then, you won't call it an innovation. It will be a great idea, but it will remain at that. For innovation, you have to go from idea to actually building something, in ways that may be unique. So, the very first part of this journey is empathy. Why is empathy important? Empathy, it means understanding and sharing the feelings of another, right? So when we look at a problem that someone's facing, we need to feel empathy. We need to really feel connected to the problem, to this person that is going through this problem, to actually be passionate enough to go through this complex journey of design thinking to implement some kind of a solution. So, empathy is a way for us, to view this world and how we can actually go about improving the world around us. Now, the second step, which is defining a problem, right? The problem is what is going to drive everything, in the journey, the process of innovation. The core is the problem that you need to solve. This is probably the single most important thing in this entire journey, right? The being able to really understand the problem, being able to really identify with the problem and empathize with the person, the people that face this problem. And this is a very core to design thinking. And the third is ideation. Ideation is, once you see a problem, the problem could be, a person who cannot see is walking around with very little support and tends to miss certain obstacles, and this could be a problem, right? And ideation is just continuously thinking about this problem and trying to come up with ideas on how you could solve this specific problem. So ideation is very important in design thinking, and it really, the core of, once you understand the problem, ideation is the process of together trying to come up with different ideas collectively to see if a solution can be arrived at. And then the last step, which is prototyping, is actual implementation of these ideas, which were driven by the problem that you identified. So with the prototypes, there are many different ways in building prototypes. This is a very core part of innovation, where something physical is being built, and a prototype, could be made out of anything. Robots could be made out of cardboard and wood. That could be a prototype, right? So a prototype is actually taking your thoughts, taking your ideas, taking the understanding of the problem, and building something that you feel is going to solve that problem in some way, right? So this is the four steps of um, of design thinking, and testing is equally important. And testing, I'd say, is present almost at every step of the journey. When you identify a problem, there are ways to test, because when you identify a problem, you define what that problem is. You hypothesize. You have different ideas of what you think that problem is, and you can test those. Test whether your understanding of the problem is actually true or not, or is it something that you believe in, but it may or may not. So there are ways to test those things as well, and I'll get into the details soon. And obviously, testing of prototypes, testing of ideas, all can be done through discussions. Prototypes can be tested in real-world environments. They can be tested in a lab. So this is a cyclical process. You once you've identified a problem, after that, innovation, is something that will continue, forever almost. You have an idea, you build a prototype, you test it, you improve it based on newer ideas, you build more prototypes, you test, and this becomes a continuous process as you launch products for users, as you build solutions for users. So the part on empathy, that and the problem, really it defines why you want to do something, right? The why of whatever it is that you want to do, whatever it is that you want to try and solve or identify, is really driven by empathy and the problem that you've observed being faced, right? So why is probably the most important part of this journey, is understanding the why behind what it is that you want to do. And what I'm going to do is I'm going to walk you through the process of how we at Fluid Robotics, before we even started the company, before we even knew what the product was going to look like, we went through the process of going through the 5 whys, asking yourself, over and over again, why multiple times, to really go deep into understanding the problem, understanding who's facing the problem. And what I'm going to do is I'm going to walk you through the process that we followed. What is that first problem that occurred to us, that we saw, and that led us in our journey. So this is the beginning of empathy and the beginning of identifying the problem, right? So the very first thing that we observed, myself, my partner Nidhi, when we were traveling, we were living in the US, working in Silicon Valley, working on jobs as an engineer. She's an engineer. We visit India, and it occurs to us, something that we've always seen, maybe ignored several times, is the question that occurred: why are Indian rivers so polluted? Right? All of us that live in any major Indian city, or even if we don't live in any major Indian city, live in a tier 2 city with fewer people, we still see rivers that are extremely dirty. So why is that? We asked ourselves this question, and we really thought about it, and we felt that we need to go deeper. We really need to understand what's going on. Hello, can you guys hear me? I just lost my screen. Hello.
Yes, we can hear you very
You
well.
can? Okay, sorry. I lost my screen for a second. Not sure why. Okay, I'll just get back. Right. So this is the first question that that got us on this journey. Now, we needed an answer to this question, right? And before we could get into any answers, there were two things that we needed to understand, and something that I'd like to explain to you as well. The first is, what are sewers and what are storm drains, right? When we use our bathrooms at home, when we wash our hands, we take a bath, that water leaves our home and enters pipes that are called sewers, right? And they're supposed to go, sewers are supposed to be connected to a treatment plant where they treat this dirty water, they clean it, and that clean water is then either used for something, or it is put back into the environment, into lakes and rivers, right? So this is what we had to understand. This is sewers. This is very important infrastructure that the government maintains. And the second is storm drains. What is a storm drain? A storm drain is again a network of pipes and drains that carry rainwater. So every time it rains, you don't want your city, your neighborhood to get flooded. So you build a network of pipes and drains that take the rainwater safely away to some water body, whether it's a lake or a river. This network of drains is meant to carry rainwater. So these are the two things that we needed to understand when we began the process of answering these questions. So, why are Indian rivers so polluted? Because untreated wastewater, which is the dirty water that leaves our homes, the dirty water that leaves factories and other industries, they enter into lakes and rivers every single day, right? So this is the first answer that we got. Indian rivers are polluted because untreated wastewater enters these rivers every single day. Now, we had to ask ourselves again, the second question: why does untreated wastewater enter rivers every single day? Why is there untreated sewage? Why is this dirty water leaving our homes, leaving industries, and going straight into rivers? So the answer to that question was because wastewater sources are not connected to a treatment plant. The wastewater that should leave our homes, the dirty water that should leave our homes, should get treated in a treatment plant, right? So it doesn't reach a treatment plant in STP. So this is what we realized, the answer to our second question. Now then we have to ask ourselves again, why are wastewater sources, like homes, industries, why are these sources not connected to a treatment plant? Right. So this was again going deeper and deeper into trying to really understand what it is that problem. Yeah. So the question, why are wastewater sources not connected to a treatment plant? Because it is easier for whoever is building, constructing buildings, industries. It's very easy for these builders or contractors to connect whatever new infrastructure they're building. It's easier for them to connect it to a storm drain, right? If you connect to a sewer pipe, that pipe should eventually get to a treatment facility. But whenever a new building is constructed, whenever some new infrastructure is built, it's very easy for whoever it is, for the contractor to connect to a storm drain. Now, where does the storm drain go? It goes into a lake, it goes into a river, or it goes in to the coastline, right? So this is what we were learning as we were digging deeper and deeper, and these were questions, that took us months to answer. It took several discussions with government engineers, with government authorities, discussions with other stakeholders, and even a lot of reading reports that are out there, Googling the state of India's rivers or state of wastewater infrastructure, right? So these were questions that took us months to really get clear answers to. And today, in hindsight, that was probably the most important part of the journey that we embarked upon. Yeah, so having answered this question, it's easier for these contractors to connect to a storm drain. Okay, now going one level deeper, asking ourselves why the fourth time? Why is it easier for them to connect? Right? Because existing sewer pipelines are old, they're damaged, and they're often overflowing. And this is something that a lot of you're out on the street, you can see a lot of times wastewater just coming out of the ground through some manhole cover and unfortunately dirtying that entire road that's near. So so this was sort of one, close to the final answer that we were really looking for. And we saw that existing pipelines were just out of shape, right? They were extremely dirty, damaged, and they were overflowing in many places across the city. And then we got to the fifth why, right? Why are they damaged and why are they overflowing, right? And the answer to this question actually opened up our eyes to what the core issue was. The issue was the fact that underground pipelines were not mapped, right? When the government did not have maps of their wastewater infrastructure. So today, if you go to a municipal corporation and you ask them, sir, where are these pipes underground? Where are the pipes? There is very little information that is currently available. There are many reasons for it, and we did dig deeper into that as well. But the answer to this question, that the pipes underground are not mapped, and when something is not mapped, when you don't know where something is, it's impossible to try and fix it, right? It's just not possible. So this answer of the fact that pipelines were not mapped and were not it was not possible to fix them really opened up our eyes into what it is that we needed to do next. Right now, we felt empathy. We really felt, oh no, like it's difficult. No matter how much a city engineer, a city administrator wants to fix this problem of polluted lakes or polluted rivers, they're just unable to. They just don't have the information. They don't have the tools to do it the right way. Right. So we felt bad that this was happening. We felt bad for the people that couldn't do anything about it. And we felt bad that the people that were suffering, were citizens. we eventually end up suffering when a lake is dirty, when a river is dirty, because that ends up spreading diseases. Diseases like dengue. You have drinking water getting contaminated. Your water source. A lot of times, if you live downstream of a big city where a river flows, that downstream city or town or village unfortunately has to take that dirty water and use it for their own purposes. They'll use it for drinking, they'll use it for agriculture, farming. So this, that the process of understanding the problem and feeling empathy towards the people that were actually struggling with it drove us to then think of the how and what we wanted to do. The process of ideating, prototyping, and testing. Now that this was the perfect time for us to get to this stage. Now we started really racking our brains on what kind of ideas we could think of. What is it that we needed to do? And we had this very clear picture in our mind. Pipes are not mapped, and pipes, therefore, they cannot be fixed. So what do? Let's build a technology that can help map these pipes. Let's figure out how we can help the government understand where these pipes are damaged, so that they can now locate and fix these damages effectively, eventually impacting the health of lakes and rivers and coastlines. Right. So the ideation process. Now, the ideation process started off on a piece of paper. Us drawing images of what we wanted to build, and this was a perfect problem to be solved using robotics. Right. This is a very dangerous environment. You don't want, if you have a pipe that's stuck, you don't want a person to get in and risk themselves to all the harmful gases, all the harmful chemicals that are present inside of the pipe. Right. We don't want to cause further damage to society, to the environment. So, this is a perfect use case to build a machine to do it. Low risk, very mundane task. It's a dirty task. Let's build a machine. Right. So then the ideation process started. We started thinking, oh, what does this robot need to do? Does it need to crawl? Does it have wheels? Can it swim? What all does it float? How do we put something inside these pipes that can help map these pipes and identify all the problems that are there? One great way is, let's put a camera inside. You put eyes inside the pipe, we'll be able to see everything. We'll be able to see where the pipe is going, so we can map it. We'll put some sensors on it. We'll put a accelerometer. We'll put a gyro. We'll put a compass, and we'll figure out how to map these pipes. Right. And then with a camera, as we're mapping this pipe, we'll also identify and locate all the different damages. If we see a crack, we know where the crack is. If we see some damaged joints inside the pipe, we'll be able to map them out, and we'll be able to tell the government that they need to now go dig right here and fix this problem, and solve whatever issue that they're having. So this was the ideation process, and the ideation process can happen on a piece of paper. It can happen in AutoCAD. It can happen in, you can use whatever tools you want, in this process. And the next step was prototyping, right? So now when you start, when you've gotten a clear, you've got your ideas clear, you want to build something, you start, thinking about what is it that I need to build? Do I need wood? Do I need metal? Do I need plastic? What do I need? Do I need motors? How do I control the motors? You start now thinking about the technology. So really, you come to technology much later in the process of design thinking, right? Design thinking, we spent more than 5-6 months just racking our brains around the problem before we even got to what technology needs to be built, what needs to be produced, right? So this is like one of the first prototypes that we built. I was back, I was still in the US. I was still working. I had a full-time job building surgical robots, and on the side, I was trying to build all of these prototypes, right, and trying to figure out if we can really solve this problem that we've now understood really well. So we started building these prototypes of robots that could map and inspect pipes. And then you test, right? We got prototypes and then we started testing them. Where do you test them? We did a bunch of testing inside of inside of a lab, inside of closed environments where conditions are more ideal, and then we looked at real world testing. Right, and this is how our testing process started. So we're putting robots into actual pipes, where the government was facing real problems, right? So this is the process of testing. Initially, we tested our understanding of the problem by talking to more and more people. We talked to 10, 15 different engineers in cities. That was the testing process where we tested our beliefs in the problem, what it is that we felt the problem was. And now in the prototype phase, ideation phase as well, we're doing more testing, right? Testing is nothing but experimentation. I have this device, or I have this idea, and I'm going to experiment whether this is actually true, whether my understanding is really true. Keep asking more questions, keep trying new things out, and really see how things progress. So after a bunch of testing, we came to a stage where now we had this robot that we were now deploying, in cities in India. So once we went through that process once, the design thinking process once, where we had tested the prototypes, where we had really, confident now that we understand the problem, we've we've got great ideas on how to solve it, and now we've built a prototype that works. All of us that were working on this, we could quit our jobs. We decided now we're going to start a company. We decided we'll call it Fluid Robotics, and we got this first robot deployed on projects with Mumbai City, right? And this is a robot working on a real job in a real environment, trying to map out this pipe that the government didn't know where it was and what condition it was in. So this was the process, and the process has not stopped. It has been 5 years since we put the first robot in, and the process hasn't stopped. We continue to iterate. We continue to improve on our understanding of the problem, on our ideas and our technology as well. And today, we've got bunch of these robots that are traveling across underground in cities, trying to identify, map out where these pipes are, help the government really try to tackle urban water pollution. And this is what we've been able to manage through the design thinking process. We started with one question of why are Indian rivers so polluted, and fast forward to 5 years with the continuous process of iterating, understanding problems further, thinking of newer ideas of solutions, building prototypes, testing them, deploying them. Through this process of innovation, really backed by design thinking, we've come to a place where we've now monitored over 1 billion liters a day of urban pollution. So this is 1 billion liters of just wastewater, untreated wastewater, that is going into lakes, rivers across 12 different cities. And this is every single day, you can imagine. So, today, 1 billion liters a day that we've monitored has gone into these lakes and rivers. Tomorrow that's another 1 billion liters a day. So this is a process that we have worked very hard to stop. And out of the 1 billion liters a day that we've been monitoring, about 70% of it, so 700 million liters a day, is now being redirected away from these drains to a treatment plant. So what you see in in this image, these are all this is all data that's gathered using robots. So this aerial view that you see here, this is taken from drones. The detailed locations that you see marked on the map, those are taken by the robots that travel. all the maps that you see in this network are created by the robots, and all this information of how much is flowing in to these lakes and rivers is gathered by the robot. The robot actually maps out and helps identify how all of these drains can be rerouted to a treatment plant and get all that wastewater away from a lake and river and send it off to a treatment facility. So this is, that process through iteration, at different stages, you may not make you may not be right every time. You may make mistakes. You may think, something's a problem when it may not. You may build a prototype to solve it, and at the end realize, oh no, I have to go back and have to rethink this, right? So there will be mistakes along the way. There will be decisions that you take that may not be ideal, but it is more important to take decisions than to sit and wonder whether you're right or wrong. It's very important. If we, on day one, when we thought of our first question, if it have just sat and thought about urban pollution and what to do without taking any action, nothing would have happened, right? We took action. We realized we made a lot of mistakes in the process. A lot of times we build wrong features into the robot. We build incorrect technologies that did not have a real application. So we did that in the process, but that the process of making those mistakes taught us what the right decisions were, right? So it's very important in design thinking to take decisions. Decisions are going to drive growth, they're going to drive innovation, and eventually get you to solve the problem that you're really passionate about. So today, after having gone through this process, we started with one question, one why. Now our robots, our technology, present in 4 different countries. This year, we've monitored more than 2 million feet of pipelines across these countries. There's, all the water pollution that we've been able to stop. And through the process of design thinking, we've also been able to deploy our technology for the current problems that are being faced globally, which is around COVID. We've been able to send our robots into these same drains and actually test the wastewater for how COVID is spreading around communities. And today we're monitoring 8 million people every day across multiple cities to track whether COVID is increasing or decreasing. Can we actually help predict the next outbreak? And all of this, has come through the process of asking yourself why as many times as you need to get to the answer that you feel you're passionate about, trying to solve the problems that are really critical to help improve this world that we live in. And you guys, I'm so proud to be able to present all of this to you and see the fact that you guys are going to drive innovation in a way that no other generation has in the past. So it's great to see all of you involved in this. So just one final takeaway before I open up to questions is really the problem is way more important than the solution, right? Being married to a problem will help you build the right technology. You can't go with, I have a robot. Now what is it what this robot can do? Let me figure out a problem that it can solve. Right? It's always the other way around. If you're really passionate about the problem, you will figure out by hook or by crook, by multiple iterations, by making mistakes, you will end up building the right technology that is going to solve this problem. And that is what drives innovation today globally. No matter what company you want to look at, it has always been the problem that comes before a solution or a technology. So with that, I'd like to thank you for this opportunity, and I'd love to take any questions that you have.
Thank you, Mr. Asim, for the talk and great insights. I hope that the participants would consider all of the things we spoke about in this session and have major learning takeaways, not only for the competition, but for their entire journey ahead. Now, I'll hand it off to Sakshi for the final part of the webinar.
I would like to start by thanking all the panelists. Thank you to all the experts on the panel across aerial, underwater, and terrestrial for their extremely meaningful and insightful discussions. Thank you to IIGF for this opportunity. And last but not least, Capgemini for their support for this event. Also, through the chat box, I have realized that some of you are still not clear about what is the phase 1 and phase 2 and how to go about it. So I'll just give you a short recap. Phase 1 starts from October 3rd to October 15th. During this course, you will have to find a problem statement in any of these three streams, which is aerial, underwater, and terrestrial, and devise an innovative solution about this problem using technology. And you will have to create a 3-minute video about your solution and the problem and how you have used technology in this. In this phase 1, you will not have to, in phase 1, you will not be required to build a working prototype. You just have to have a clear idea of what is your problem and what is your solution. The video can be either an animation or a live action. It can be any kind. Just make sure you're addressing a problem and creating a solution. After this, on 18th of October, the judges will judge all your videos and declare the top 30 teams that will move on to phase 2. In phase 2, you have to further work on your solution and figure out more about the model, how does it work, what factors or resources you will require it for implementation, what kind of technology is used. You could further develop on your solution and create a 10-minute presentation, which would be shown or presented to the judges on 30th and 31st of October over a Zoom meeting, along with a 5-minute Q&A at the end. The main evaluation criteria is innovation, practicality, effectiveness, how will you implement it, economic viability, and sustainability. So this is an overall review of what the entire competition is. So now I hope all of you have got some idea of what could be a possible problem statement and solution. Also, please note that you could pick up a problem statement and devise solutions that were not discussed by the panelists, but do keep them within the aerial, underwater, and terrestrial streams. Please do refer to the website and Instagram pages for latest updates and announcements. And please do not hesitate to write to us if there are any questions whatsoever. We will be also updating our FAQ section on our website frequently. Thank you once again, and remember, your ideas can impact the world. All the best, and we look forward to going through your ideas and submissions. For updates, follow us on Instagram at trailblazer.global. Keep checking our website for further information, theinnovationstory.com. Thank you and have a great day.
Your PPT should be posted on a link which will be provided on the website. Just make sure that you check our website regularly so that you can check when the submission portal is on. The website is theinnovationstory.com. You'll given a link before the submission actually happens. Thank you all for attending this webinar. I hope that this was helpful. Please make sure that if you have any mail us at reachout@innovationstory.com. Great day. Bye. If the website if the website is not working, we'll send you the link on mails. Make sure that you access the website through the link that we send you via email.